Okay, thank you for joining the lecture. And today I would like to talk with you about some nonlinear models. Last time when we talked about nonlinear simulation, so we do some prepare work compared to the traditional Newmark's beta method. We use acceleration-based Newmark beta method and use IMHART, AVAA. Instead of that, we used incremental acceleration-based method. And also we use directly using restoring force to calculate. And here's the difference between them. So inside here, we have restoring force-based model here, so that we can using some function to calculate some nonlinear force to instead of them to directly calculate these models. So actually, until now, we using a linear relationship of displacement and restoring force F. But in actual structures, they are, in cases, highly nonlinear hysteresis of displacement and force relationship. If you load it using earthquake-like cyclic loading waves. Cyclic loading, this means that you have one time a yielding displacement, you go the positive direction loading, and then go to the negative direction loading, and then come back, and then do this a few cycles, and then I use 2 times of yielding displacement and loading, and then until the structure is damaged. You do it like sine wave loading, like cyclically loaded the structure. So the hysteresis curve is like some hysteresis curves is like rounded type, right? Rounded type, right? So the real loading test, we firstly simplify this model using the like monotonic loading, just push over one direction loading, right? So we would like to see something nearly, we like some curvely increase at some point the yield, and then the whole cross-section yield and the force and displacement relationship gradient comes lower and lower until to the horizontal. So this phenomena is called, we call yield. So in yielding, so in yielding structures, their gradients decrease. We call this softening of the stiffness. So this difficult to using one line to express them. So we use mostly, in most cases, we can use 2 straight line to express this kind of displacement and force relationship. Like one is elastic, the other is plastic. So between the elastic and plastic, they have a point of yielding point. So before the yielding point, we use elastic stiffness. And after the yielding, we can use no gradient, 0 stiffness, or they keep the plastic yielding force to there. Or we can have some gradient on that. We call this region as elastic domain, and here is the plastic domain. The boundary is the yielding point. So we call this kind of case, after yielding, the relationship of D and F is a horizontal line. Force no longer increase, right? Perfectly deformate in plastic, okay? Perfectly deformate in plastic. So that we call this kind of model, we call it perfect elastoplastic model. So they have the elastic part and perfect plastic part. No strengthening, no hardening effect. just like this. So this is a perfect elastoplastic model. Or sometimes they have some second gradient. Second gradient, we call this elastoplastic model. This is the more Euro models, right? So they have the second gradient. But this is only in the case of monotonic load, pushover load. But real case, we show that it's cyclic load, right? So I will introduce firstly the bilinear model, which can both do elastoplastic model and perfect elastoplastic model. And we have both first gradient and second gradient. And they can also predict the here's the loop of loading, right? Plastic, positive, negative, this cyclic loading. So bilinear model is basically like this. So you can see that they have three parameters, which is dy, which is yielding displacement, and fi, which yielding force, and alpha. Alpha is the stiffness ratio of after yielding to before yielding, right? And the second stiffness is alpha time of first stiffness. It means that alpha is the ratio of second to first stiffness, or we say how much we discount of the stiffness after yielding compared to the initial stiffness ratio. So generally, this value is about from 0.1 to 0.5 for general structures. And they have two status. One is elastic status, and the other is plastic status. So in elastic status, so whenever you're loading and unloading, right, it's almost linear. Almost linear. Use the stiffness K1. Sorry. And we have two events here. Changing from two status. One is yielding. Yielding means that you come from the elastic status to plastic. So the other is called unloading. Unloading means that you from the plastic domain you loading to different loading back to the other direction. In that case, you will come back from the elastic domain, from the plastic. We call it unloading. So yielding is changing from elastic to plastic. Unloading is changing from plastic to elastic. So once you yield, unless you load it to the other direction, so there's will not be changing back to their original stiffness. Okay. So let's see the parameters. The dy is yield displacement. So because the loading is in two directions, positive and negative, two directions, so we have two yield displacement here. First is yield displacement is one time of dy. The dy2, the negative direction, is minus dy, of course. Same with yielding force. The yielding force, it is also have two direction. The first direction is the fi, the negative direction minus fi. So between this point and this point, they are in the elastic domain. So they loading and unloading without any changing. So nothing changes, almost linear, very simple. So in this elastic domain, the stiffness K1, which is dFi divided by dy, Fi divided by dy. Right? It's the ratio of displacement and force. So K1, K2 is a plastic domain stiffness, means that they will be lower than the first stiffness, right? Elastic states. So they use ratio of alpha to define that. So there's 1, 2, 3, 4, 5 parameters. But before we said 3 parameters, right? So for bilinear model, this 5 parameter can be calculated to each other. So you just need to know 3 of them. You can calculate all of them, not any 3 of them, right? For example, you know dy and fi and alpha, so you can calculate k1 by fi divided by dy and k2 by alpha by k1, alpha times of k1. So just know alpha, dy, and fi. So there's another value called QC we will talk about later. So generally, you know K1, QC, and alpha, you can totally calculate all other parameters. So in the beginning, between dy and minus dy, whenever structure how loading, there's always stiffness always becomes K1. So we call this status 1 or say elastic status. So no worry about anything about this. And we define the right side is the dy1, left side is dy2, which is dy1 equals dy and dy2 equals minus dy. However, once the force is larger than the yielding force or displacement, loading displacement is over the one of the boundary, the 2 boundary, dy1 or dy2, or say dn plus 1 steps displacement is larger than dy1 or it is smaller than dy2, the event of yielding will happen. The yielding happens means that k will be changed from k1 to k2, k1 to k2. Okay. So another event will called unloading. So when you once you in the plastic domain, right, plastic status, so you're loading this direction, it's okay. But once the velocity changed from positive to negative, or changed from negative to positive, like this, originally you are going to the positive direction, but suddenly you change to this direction, then we know that you are in unloading. And stiffness will change back to elastic stiffness. Also, we need to update dy1 and dy2. Why I will explain later is because we're using some called hardening rules. So this hardening rules tell us that how this elastic domain changes after loading. So we need to update dy1 and dy2 here. Same once we load here, we check dy1, dy2 here. So how to change dy1? We if we are in the positive direction loading, unloading to negative direction, like this figure shows, we're here and going to here. So what's going to happen is that in this domain, we'll still keep the elastic, but from here it will be yielding. But before the yielding point is here, dy2 fi. Now we change to here. Now we change to here. So how we decide? It? So we keep the distance between these 2 points, the displacement and the force, same distance. So from here to here, displacement or elastic domain, the span of elastic domain is always same. Because K1 is the same, right? K1 is the same. So once displacement is same, it also means the force is the same. So what changed is just the center of elastic is changed, shifted because of the plastic domain loading. So we can use so how much we change? We use the structure that the unloading point. This unloading point is most loaded point, right? It will be our new boundary of elastic domain in positive direction. So in the other direction, I just calculate it from the span of the elastic domain, which is 2 times dy, right? Here is originally dy1, dy2 is here, positive dy, negative dy, where this is 2 times dy. So same. So new dy1 is here. So the new dy2 will be 2 times dy smaller than this. Same with the negative direction. Originally, we were in here, so we just updated dy2, new dy2 to be here, equals to dn. dn is last time's loading before unloading, right? This time is dn plus, so it already been loaded from here to here, right? So so here is dy2. dy2 will be 2 times in the right side plus 2 dy to decide the new dy. So that's how we uploaded dy. So there's also very a small detailed difference between the velocity change and the displacement change. But here we can roughly consider that Vn we calculate from delta d. So delta dn and delta dn plus 1, we change this to check this are they positive or negative, so that we can decide unloading or unloading. There's a little bit different between velocity and the displacement. So the displacement is, the velocity is the moment, right? N plus 1 times delta t, this moment's velocity. So actually, sometimes this moment of velocity becomes negative, but actually delta dn plus 1 is not in changing to the other direction. There's sometimes this happens, but here we just ignore this progress. So if you're using the method I teach you in this lecture, so you need to be worried about this kind of problem. Okay, so now we have the binary model. We know that the two status, elastic status and plastic status, the two event yielding unloading, and we'll change your status and update the elastic domain. Okay, so I summarize this in here. The status is 1 yielding, 2 unloading. The condition is larger than dy1 or smaller than dy2. The unloading is Vn multiplied Vn plus 1 smaller than 0. And what we change is k equals k2 and k is k1, and we also update dy2. So I summarize this in this bilinear, okay? So let's go through this first. So we do from n equals 1 to the end, right? To the end. So firstly, we in the beginning we say k equals k1, right? And we will check if it is yes. Initially is k is k1. Then we go to check dn plus 1 is larger than dy1 or smaller than dy2. If it is no, and then we don't do that, nothing, right? Yes, if yes, we will change to plastic and go to the next step. If no, then we just go to the next step. Let's go to the next step. And so if it's not equals k1, we go to checking if they're unloading. Here I use incremental displacement to check. If yes, now unloading happens. So change back from k1, and we will update dy1 and dy2 using this progress. So and then we check is I'll calculate the force. Calculate the force. Force Fn plus 1 equals Fn plus k third n plus 1. And then we go to the check is n equals the total number of the analysis step. If not, finish. Yes, go again. Okay. So let's see how to program this in Python. So what we left behind in the last time is something like this. So we're going to do a little bit of programming here. So F5 linear model. So firstly, we need to a loading displacement. We need some loading displacement. So how to do that? We just firstly, as we anytime we did before, firstly we will setting some parameters for doing some sine wave. Right? Sine wave. What we do is that we have 100 point calculation point. Sigma equals 1, alpha equals 0.1, dy equals 1. And mu is the maximum amplitude. So the amplitude will be mu multiplied by dy. So ky equals k multiplied by dy. QC is the critical force, and we'll talk about later. Okay, and then we need to generate the displacement. We use NP range to generate some displacement, and with also changing the amplitude, right? Changing the amplitude. So y will be a sine wave of the amplitude, and so A will be the amplitude that changing from small to larger, and D will be the displacement we give them. Okay. So firstly, let's forget about the amplitude changing. So in the beginning, if amplitude is 1, it'll be like sine waves, right? So we have 100 and 2 pi. So let's see x and y. X is a time, right? X time. So y is some sine wave. So right now we're changing the amplitude from small to large, right? Based on 1. So the amplitude will changing something like that. So we have a gradually loading displacement. And then we do then we will try some bilinear model. But this is a naive ones using this flow chart of loading. So when we're loading them, firstly, we need to define a function, a bilinear model. We call it bilinear naive. We use u and un and then dun. So u is displacement here. We use a little bit differently. We use u. And f is last steps of force. And alpha k qc is a parameter for nonlinear. And s and dy and dy1, dy2 is the status we have here. S means once means a statistic. When s equals to 0, it means elastic. 1 it means plastic. Okay, and also we setting the dy1 is One is the displacement, yielding displacement of the positive side and negative side. So firstly, we know nothing, so we will calculate f equals to 0. F is fn plus 1 here. Du is the delta d. This type's displacement to last time's displacement. Okay, so let's do this check. So if s equals to 0, which means elastic, right? And we say f equals to fn plus du k. Okay. And but we will check if u is larger than u by 1, or else if u smaller than u by 2. Else if. So if one of them do so, then I would say s equals 1 become plastic, and f1 is equals to fn plus d1 minus un. So this is a place that before loading, right? Before the loading, for set until loading with multiple k. And then is loading, right? Then is after loading part, right? After loading part. So so f is equals to f1 plus u minus dy1 multiple alpha. Okay. So s equals 0 means k equals k. S equals 1 means k equals not equals k. So this part is just the same. I just change them to S1, but this is S2, S2, change S2. Fine. Okay. So then let's say S is not equal to 0, which this means S equals to 1 is in the plastic status. So the function will is similar with this one. So f will becomes to the f will becomes the multiple alpha multiple k. And what we will check is that check is dun multiple du is smaller than 0 or not. If so, we will do s equals to 0 and fn equals to fn multiple du multiple k. Calculate just like elect domain. And we don't need this anymore. But we need to update dy1, dy2. So we say if du is smaller than larger than 0, larger than 0, and d by 2 here. Let's check this, right? So dy du is larger than 0, right? dy1. Okay. So this is the inverse, right? So if du is larger than 0, so right now we're going to positive direction. So before we are negative direction. So we're yielding from the negative direction. So dy2 is equals un. dy2 1 equals un plus 2 dy. And else, so dy1 equals to un, and dy2 equals to dy1 minus 2 times of dy. dy here is the function. Until now, so we finished. Now we return what? F du s dy1 and dy2. Okay, so by doing this function, so we should be able to do a simulator, which is a simulator function of bilinear naive, and we have the initial condition of dy1 equals dy, dy2 equals minus dy, and f is the list we're trying to get. D is the input value, which we generated from here. This D. And then we use the step-by-step step of in the list of D. We cast D to the list before we generated NPi array, right? So we cast them to the list. And then we use naive bilinear model to calculate the force and record step by step and append force. And then we suddenly return force. Okay, so let's see this works or not. Okay. Okay, so we can get the force model, but let me try to make them to the black color. Makes cooler. Okay, something like this. And maybe I can use the function plot function we recorded here. Plot x1. Right? So I just use plot xy, d and f that we generated last time. Right? Oh, so it's looked better. So if you didn't follow the program, so don't be worried, because we're going to teach you something better, simplify bilinear model. So the bilinear model we teach you here is one of the very fundamental step-by-step way to do that. It is there's a lot of models that based on linear bilinear model. So you need to learn the step-by-step approach of this kind of if and else, elastic domain, plastic domain, the condition that just set them one by one, something like this. So it works. But for the case of bilinear model, because it's very simple, so they have we have very simplified method to do this simulation. That's why a lot of people love to use bilinear model, because they have they can programming very simply. So we're asking that, do we have a simple way to do that? So when you analyze the results, right? The result, you see it look like this, right? It look like this. So what is the special feature of this curve we see? We see that every time cyclic, they're always passing through the same point here. Always passing the same point here, right? Here. whenever the amplitude is, they always pass this point. They always pass this point. So what is this point? We say it is a critical point, which is the cutting the cross section of when d is 0. Is the force at d0. Whenever you do what kind of loading, if it is plastic domain, you're passing the here, you always get this force. So this is we call it critical force. For shear model, we use Q, so we use this name QC, not FC, right? Remember, QC is a more general name for the critical force. So the critical force, what is critical force? Is we can see here is Fi. Critical force is a little bit smaller than Fi, yielding force. So how much smaller is this smaller, right? This is, what is this? What is it? See this triangle? This triangle. So remember the gradient of this line is K2. The horizontal displacement is dy, right? So the force is Fk2 multiple F dy. Okay, so from Fi, just divide this part. We can get the critical force. Okay, or we can say Fi divided by this part is also can be calculated by change Fi to K1 dy. And what is K2 is alpha times K1, right? So we can get 1 minus alpha times K1 dy, which K1 dy is Fi, right? So it's 1 minus alpha times Fi. Or say this is alpha K1. So alpha K1 dy Fi. So 1 time Fi minus alpha times Fi. So it's 1 minus alpha times alpha. It's called critical force. So critical force is the same when there's no second gradient. So K2 equals 0. Or say alpha equals 0. So QC will becomes Fi. I consider that at this time, right? So in this kind of alpha equals 0 case, so we call this perfect plastoplastic model. So for this model, so what is different is everything was change the angle of K2, rotate the angle of K2, everything rotate the angle of K2. So maybe we can split this one model to two models, okay, something like this. One is just K2, it's just linear model. The other model is the force derived from this model. It's just rotate from original to this one. So this one is a perfect elastoplastic model. Okay, so it is perfect elastoplastic model. So, so you can consider that something very interesting. For example, the second stiffness, of course, is 0. And what is first stiffness? First stiffness is everything rotated to the K2, so it's K1 minus K2. So it's K2 minus K2 is 0, and this is K1 minus K2. So why we use perfect elastoplastic model? Because perfect plastoplastic model have a character that very easy to calculate. And this one is also very easy to calculate. So we focused on this one, and we see that in the beginning, we just calculate the elastic model, right? Elastic domain by K1 minus K2, the new elastic force. And here is our boundary of QC and minus QC. So for perfect elastoplastic model, it never going cross the boundary. Upper boundary is, high boundary is QC, low boundary is minus QC. So we never cross that boundary. So however, we just linearly calculate. Just check once it was larger than the boundary. It just put it back. make the force equals to QC. So we call it FE, elastic part. FP is the perfect elastoplastic part. So the perfect plastic force will never go larger than QC or smaller than minus QC. So we just calculate it anyway and check it. When it's larger than QC, make it equals QC. When it's smaller than minus QC, make it equals to minus QC. Will be fine. So by doing so, we can calculate every step by step. Just make it larger and becomes. We don't tell you are in plastic or you are in elastic domain anymore. We don't do that. Every time we just calculate if larger, put it back, larger, put it back, larger, put it back. Whatever, how many steps do that. So you can do calculate, do that. So once you're unloading, you're still following the equation of using this gradient, right? So, but it will not larger than this or smaller than. So it will naturally calculate this straight line. However, once you are larger in that side, and you will also naturally calculate it by going up and put it back, going lower, put it back. And then you can do calculating smoothly to the hysteresis curve as many as you want. So just remember that for the whole model, we change them to elastic part and plastic part. The elastic part, every time we calculate, just use this time steps, displace multiple K2. We go through this line. For plastic part, I used last time a plastic force plus the delta D and multiple the gradient. Okay, I do one if. If it's larger than 0, P, if it's larger than 0, we check, take the minimum from QC and this one. So which means smaller than, right? Like if they're larger than QC, I'll take QC. If they're smaller than 0, I say this is the largest one. Okay, this one. If smaller than minus QC, then I take minus QC. So then you can calculate FE and plus 1, then you just use FEN plus 1 plus FEN plus 1 will be F total F. Okay, so we're using this equation. Let's do advanced, or say not so naive, right? Simplified bilinear model. Okay. So for simplified bilinear model, we just call it define a bilinear model. I use U, UN, Fn, last steps force, K of alpha of QC. Okay, this parameter we're going to use. So du is a displacement increment is equals to U minus UN. We need to use. So Fe is equals to K multiple alpha multiple U. And Fp is from Fpn plus 1 minus alpha time of K multiple du. However, we don't have Fpn, but we have Fn, which is last F4. So we know that Fpn is equals to Fn minus Fen, right? And Fen, same with this one, just last step's displacement. Then we calculate Fpn, and then we calculate Fp at this step. Now I just do if, right? Np dot absolute value ABS absolute value of Fp if it's larger than QC, right? Whenever it's positive, negative. So let's FP equals to the QC multiple the direction of the FP before. So we say use the FP divided by NP dot maybe absolute of FP. Then it will give you the direction automatically. And I say F equals to FP, FE plus FP, and return F. So simple, right? So simple. And then we do the simulator again. Do the simulator again, right? And we also using the DF, then we can see the perfectly we get displacement and force relationship of the bilinear model. Use the advanced, simplified way. Okay, I would like also to spend a little bit time on other nonlinear models that is quite useful for you, I hope. And for example, firstly, trilinear model. So bilinear model is very simple, but they have only two gradients. So for actual force, we can see that it's more complicated. They have yielding and something, right? For this case, they have the gradient that is lower than the positive direction, force going down, right? This kind of model, we think use trilinear model is better to simulate like structures hardening effect or structure softening effect, stiffness effect, like local buckling caused lowering of the force, right? And it's more better. Or we have some like rubber bearing to have some hardening effect, third degree is really even larger. Or we just smoothly simulate the curve, the gradients going to lower smoothly, not by one, but by two plastic grade. So the before the third gradient, right? So we say there are 2 points, D1 and D2. Between until here, this is just bilinear model, just bilinear model. So you don't change anything. So unless we either change it to D2, then status go to 3, number 3. So K becomes K3. And once you unload it, right, you need to calculate the new elastic center. So we explained before that we used the hardening rule that change the elastic domain didn't change. So we keep the same principle here that they didn't change. So between the dy1 positive direction and negative direction, they always center DC. So what is DC? Actually, you can see that DC moves through this line whenever how you load it here. DC always falling to this line. Okay, so this is DC, this is FC. So this is the line of the elastic force, K2. So if you see the character, this is K2 of this line. It's parallel with the K2 line. So we just calculate the DC from the dn, which is dn minus DC, or this direction is dn of DC. So to decide this size yielding point as a second yielding point based on history. Okay. So you can keep the boundary of F high and F low for the second one, just similar with the rule of the QC rule, but this is just for the secondary stiffness to keep the secondary boundary really to calculate this. So this one is critical force point for this third gradient, larger than this. So it's smaller than K2, F2 by the K3 multiple D2. So it is F2 minus D2 multiple K3 to get its force. So the F high will be the force of K3 multiple D plus the Q3, the QC, and this one will be minus QC. Just keep them into this boundary, and then you can calculate the trilinear model very smoothly. So let's see some example of the trilinear model with firstly let's with some 0 third degree. Which number? Okay. The 5.04 trilinear model. First, let's do a very simple one. So a training model with 0 beta, and just you do a bilinear model, and then if the force is larger than Fm, then you will put them to Fm. Okay, same with the bilinear rule, right? And we do some simulation. We need D, K, alpha, QC, and Fm, which we need to set. We need to set in the beginning. So I have some parameters. K is 70.2, alpha 0.2, dy is 1, Fy is K multiple dy, and we calculate it from EF and FF and do the simulation. So Fm here is the from Fy, here is Fy, right? Plus mu2, mu here is the gradient times of displacement to this displacement. So mu minus 1, so 1 times dy, so dy, 1 dy, so multiple K2 here, so we get this force of F2. After that, gradient is 0, okay? So F2 is gradient 0. So we can check. Oh, simulate this one, right? So the second gradient is 0 type. So if I say mu is 1.5 smaller, or say dy is 0.5, right? Sometimes you can simulate something like this. You can get a trilinear model. Or you need some training model that is the third gradient is not equal to 0. So we will need do something more. So firstly, we need to calculate F1 and F2 like this, and then you should calculate F3 n and F2 n, which is the a boundary, right? The third force. So Fm is equal to this one. Then you calculate for bilinear model, and then you calculate the trilinear model with force 0, and then you can calculate the F3, which is linear gradient here. This beta is K multiple u, then plus them together. So you just return everything back to a little bit to here and calculate a bilinear model and calculate a 3D model with zero gradient, zero third gradient, and then put them back. But K1 and K2 will always be for the bilinear model, the K1 and K2 will be minus the third gradient. Will be fine. Then you can simulate an advanced way of treating a model. That a training model have a third one. So the alpha is 0.1, D1 is 1 time, which is D1, mu is 2 times, and then you yield. And then you have the beta is smaller than this. And let's try a little bit larger than this one. How about this one? So here is a training model that we can have one. Even you can have a minus gradient of this one. We can have a minus gradient, or you can have a gradient larger than the first one, which is the hardening effect model. You can simulate. Or maybe it's too small. Okay, so this linear model. So we have one last thing to talk about is Bokun model. Bokun model is a more smooth model. So I think there's a lot of knowledge to be told in Bokun model, but basically it's similar with bilinear model, but with part of that of the trading Bokun model, so that it can be accumulated by a more smooth curve. So you can see this part is linear, this part is nonlinear, and we just calculate z every time, then stack them together, it becomes bilinear model, but with curved bilinear model. So what is z? Just take a more detailed of this. Right now we used a gradient of z to time t, but they use partial differential equations here, but we just use an incremental step to see this. So z dot is delta z divided by delta t, and velocity d is delta d by delta t, and delta d by delta t, something like this. So in the two side, we know delta t is all positive, so we can delete delta t in the two side. And also we divide two sides of delta d, right? I will have delta d, so we divide them. So you can see this part becomes nothing, 1, right? This part still keep, and we call delta d divided by delta t, delta t divided by delta t. And this one just vanished, this one, right? So it becomes more slim to here. And we can do a little bit change if you like, because delta t can be deleted. So it becomes absolute of z, multiple z, and delta d absolute divided by delta d. We did a little bit before using this technique, using absolute of delta d of fp divided by fp itself. So it means that only express the signature, the positive or negative of the value. So it's 1 or minus 1. It's only 2 values. And z, we can put a z square out of the equation. So when it is out, you can see they becomes the direction of incremental of d and direction of z. Z in the initial is 0. It's 0. It's growing and growing and growing until something down. You can see in the beginning, z is 0. Here is d, when the beginning, so Z is 0 and D also 0, right? Delta D is a little bit value. So we can see in the beginning, Z is almost 0. So this part, we can ignore this part. So we can see the relationship of delta Z and delta D is A. So A will generate use 1 as the value is 1. So they increase linearly. So however, with increase of Z, this becomes larger than A should minus something. So this gradient become smaller. We can see the gradient becomes smaller. So in some point, because gradually becomes smaller, so in some point, the gradient should be 0, almost 0, near to 0. It will not absolutely be 0, but near to 0. So what is this case? Let's take a look. FT still become this one. So in the beginning, because Z is equals to D, so if we put them into that, so it's a K1D. So the force displacement relationship is just linear T, right? And gradually it increase, and finally the gradient becomes 0. So when the gradient becomes 0, we call this kind of Zn. This value we call Zn, which is maximum boundary of Z. And this equation becomes 0, so Zn is some value, right? And this is just 1 and 1, right? Because they are in the same direction. Delta D is positive, Z is also positive, so it becomes 1. So beta becomes beta plus gamma multiple Zn squared becomes 0, A minus 1. A is equal to 1. So we can know that Z power square is equals to A multiple divided by beta plus gamma. Zn equals root A minus beta gamma. So we know this relationship. So we know Zn is actually equals to dy. Zn equals to dy. So Z will from 0 to positive dy and to negative dy. So Zn is boundary of the Z, which is the yielding displacement. So beta, so A is generally becomes 1, and beta plus gamma will also becomes the decided dy. So beta gamma is smaller. Generally, beta and gamma is a positive value, and in most cases we consider beta equals gamma, and beta equals gamma. In this kind of case, it will be unloading using the A equals 1. So when unloading happens, Z still positive, but delta D becomes negative. So it's beta minus gamma. So if beta equals gamma, so beta minus gamma becomes 0. So this part becomes 0. So they always unloading using A, which is 1. So using the initial stiffness to unloading. But once Z also becomes negative, and again, the gradient decrease smoothly, like exactly this curve with this curve until go to the negative Zm. So this is how this works. So beta plus gamma should not be smaller than Z, smaller than 0. It should be, the safety way is both be positive. And there are some decided the yielding displacement. So beta plus gamma, A for this case of A equals 1, so beta plus gamma decide yielding displacement. And the ratio of beta and gamma, what they decide? They decide the shape of this curve, the shape of the becomes smooth earlier or faster. Right? is the ratio of beta and gamma. If it becomes 1, so it is most normal case. So we like use this case. Sometimes this is not Z's power, but we use some other parameter, C or something, right? So they can also some parameter related to the curve from like negative to that side. Okay. So I now show you the programming part, but I would like to simply introduce another model, which is cloth model, which is very useful for concrete structure. Cloth model have the effect of degrading of the stiffness. Firstly, they are in the elastic domain and then yielding. Once they're yielding, when they unloading, they first unloaded to 0 using the K1 initial stiffness. After that, we remember this point, most positively loaded point, du and df plus. And this point is d0, which is the force of 0 from this point to here. And from here to the negative part, yielding force, they are yielding force, yielding point, pointed stiffness. So this part, this stiffness is not decided, but decided by how they're yielding to this one. So this is called stiffening gradient. So they are not going to the yielding space because once they have developed some plastic, means for the concrete structure means there's cracks developed. So this gradient should be smaller. So they directly more pointed to yielding force. But if they go back before they go to the yielding point, so still they pointed unloading by K1, and from this point they pointed to the maximum point, not the yielding force anymore, but go to the maximum point they have. And if they successfully loaded to yielding, then they use the K2 of the second stiffness. And if they unloaded, then unloaded to using K1 to 0 and also pointed to the maximum point of active part. So they do this kind of cycle loading, but they always pointing to the, after unloading, they just directly point to the most loaded value. This is a very popular model, of cloth model developed by Clough in 1966, very old model. So a lot of papers using this. Okay, so this is all the contents I have prepared for you. Thank you.